All right, section 9.1, in fact, all of chapter 9, we're going to talk about sequences and series. So we're going to start with sequences in section 9.1, and we're going to talk about sequences of real numbers. All right, so to start with, a sequence is a function whose domain is a set of integers, starting with some integer n sub 0. It's often 0 or 1, but it wouldn't have to be. And for example, a sequence might be the sequence a of n equals 1 over n. And if you have n equals 1, 2, 3, then you have 1 over 1, 1 over 2, 1 over 3, 1 over 4, and so forth. Now you guys have seen sequences before. The first term we call, something's typoed. Oh, it's just missing. The 1 over 1 is considered the first term. We also call that n sub 0. And then we call the general term as the a sub n equals 1 over n. What the part that looks like the function is what we call the general term. But we don't usually have this notation written. That is the a of n notation like you see in algebra and trig and in calculus so far. For sequences, we generally use a subscript notation, so it looks like a with a subscript of n instead of a of the n as function notation. Can I go to the next slide? Are you guys good? All right. Now, I know you've probably seen factorials before as well, but just in case it's been a little while, a factorial with the n with the exclamation point is defined as the product of the first n positive integers. Your book actually writes it as 1 times 2 times 3 all the way up to times n. A lot of books will write it in reverse order instead, so they would write it as n times n minus 1 times n minus 2 all the way down to the 3, 2, 1. So it is the same thing, it's just a different way of sort of looking at it. And in order to make everything work out well, we actually need a definition for what 0 factorial means, because obviously we can't do 0 factorial that way. I just did n factorial because it's not a natural number. And so we define 0 factorial to be the value of 1. Okay? All right, so the first thing we're going to do is we're going to take a sequence, and we're going to write out the first, in this case, 6 terms. So we're going to find a1 to up to a6 of the sequence a sub n equals 4 over n factorial. So a sub 1 is the first one. So what we're letting this be is we're letting the n value be 1. So we have 4 over 1 factorial, which would be the value of what? That's just 4, because it's 4 over 1. All right, so in a sub 2, we have 4 over 2 factorial. Now, it happens to be that 2 factorial is just 2, but it's because it's 2 times 1, of course. So the second term is actually going to be the value 2, right? The next one is a sub 3. So now I have 4 factorial over 3 factorial, but 3 factorial is not 3. 2 factorial is 2, but 3 factorial isn't just 3. We actually have 3 times 2 times 1. So we end up getting 4 over 6 on this one, which reduces to 2/3. All right, a sub 4 would be 4 over 4 factorial. Do remember you can't cancel a factorial without actually working it out first. That's not a process unless there was a factorial on top that identically matched it. We don't have that here, so we're going to have to write out the 4 times 3 times 2 times 1. And the 4s actually will simplify here, but what do I end up with still on bottom? Yeah, so this is 1/6. A sub 5 now is 4 over 5 factorial. So we have 4 over 5 times 4 times 3 times 2 times 1. Nicely enough, from here on out, the 4 is going to cancel with the 4 that's already there, right? So I really am ending up with only the 3 times 2 times 1, which was the 6 I had before, times the new value 5 on this one. So this fraction ends up being 1 over 30. And then the last one that we're asked to find on this one is a sub 6. So I have 4 over 6 factorial. And much like the last one, the 4 will cancel with the 4 before. And I actually can think about this as taking the last value, which was 30, and multiplying it now by the additional number 6 that I've got. And so 6 times 30 would be 180. So this is 1 over 180. So you can tell, obviously, that we could do this process repeatedly, at least in theory, forever, right? There's no reason I couldn't continue doing this process. Your book, I believe, just asked you for the first 6 terms, so find the first 6 and then you can move on. You don't have to show me all of the work that I just showed you. I'm okay with you not showing me all of it, but please show me something so that I don't think that you just let your calculator do it all, okay? So show me at least maybe the first step where you're plugging in the value and then the final answer is okay. But I want to see that you are actually recognizing that you've put things in, because your calculator has some great capabilities, and we'll explore some of those as we go throughout the semester. But I do want you to understand the mathematics behind what's actually happening too, okay? All right, we're going to go the other direction. So in the last problem, we took a general term, 4 over n factorial, and we found some specific terms, a1 through a6. Now we're going to take some specific terms, and we're going to take a look at finding a general pattern for how that happens. So the specific terms we have are 1/8, -1/4, 1/2, -1, and 2. So it's often given, depending on the books you've seen that I've seen done, where they just write out the terms in order instead of actually telling you A1, A2, A3. And sometimes just because we can sort of ignore the notation part of it, it's a little easier to see without all the A's with the subscripts. So the question you need to ask yourself too is, what's going on? How do I get from one term to the next? What's happening? So tell me, what do you see? Okay, so from one term to the next, we're multiplying by -2. Whoops, I forgot my negative. Is everybody good with that? Okay. We're actually going to write this in a little bit of a disjointed way, because it doesn't always work out very nicely to have the negative associated with the 2. So I'm going to write the -1 and the 2 together, or just separately like that, because the exponents we put on there may or may not be convenient to have them combined. They may, but they may not as well. So do you remember from math courses in the past what kind of a sequence does this, where it multiplies one term by the next one to get to the next term? Do you remember? Okay. This is actually called a geometric sequence. If we were adding one term to the next, for instance, if I had 2, 4, 6, 8, 10, and we were adding 2 every time, that would be called an arithmetic sequence. And the formula or the process by which we write an equation for that works differently. So what we're really wanting to do is we're really wanting to write an equation for how we get from one term to the next. Does that make sense? All right. Because it's geometric, the equation has a very nice closed form. Now, you mentioned, Micah, that you're multiplying from one term to the next. So this idea of something being repeatedly multiplied is actually an exponential, right? If I multiplied by something 3 times, whatever I multiplied by, I could just cube it. Right? 2 times 2 times 2 is 2 cubed. So this is a geometric sequence because of the multiplication, so it means we're going to have something raised to a power, and in particular it's going to be that -1 and that 2, because those are the things that we're multiplying by. I'll give you an equation that sometimes you see written down for these in a minute. Let's see if it's on the next page or not, I can't remember. No. To think about how to do this. The other thing that you need to know is you need to know where you start. Right? Because I could do this multiplying by -2 every time and have a different sequence if I started with the number, say, 10. Right? 10, -20, 40, and then so forth. Or you know, I could do it that way too, but I didn't start at 10. I started at 1/8. So that 1/8 is also a part of what's going on. But I'm not multiplying every time by 1/8. I just need to start there. Does that make sense so far? Okay. What we're actually going to do is we're actually going to have written down here, this is a sub n that we're finding. Oops. And what we have is we have to actually think about putting a superscript or an exponent here. And so I'm going to start with an exponent that's not going to be quite right, and we'll talk about why it doesn't work and how to fix it. We know we need an exponent. Well, I've got an exponent now. This exponent won't work because if I put in the subscript 1, right, n equal to 1, first of all, the value would give me a negative, right? Well, it doesn't start out negative, right? This sequence starts out with a positive 1/8. So this doesn't give me, I shouldn't have a negative to start out with. The other thing as well is that if I had the 1 in here, I would actually start out by multiplying the 2 times the 1/8 to start with. So I wouldn't start out with 1/8, I'd start out with 1/4. So that's not good. So what could I do to fix both of those issues? I can fix them in the same way, actually. I can make it n minus 1. Now, it's convenient to think about this n minus 1 on the 2. I'll put it on the other one in a minute, so I'm not finished. But if I put the n minus 1 on the 2, what will the superscript, the exponent, what will it be? It'll be 0. And what happens when you raise it into the 0 power? You get the value of 1. So it sort of eliminates that from the very first term that we're talking about. Does that make sense? It happens to work very nicely with the negative 1 the same way. Now, the negative 1 wouldn't have been a good place for us to start the discussion because on the negative 1, I could put an n minus 1 on the exponent, or I could put an n plus 1 and it would have the same effect, right? Because it's just going to change the even or odd nature. Does it start on every even term or does it start on every odd term? So because I already have an n minus 1, it's most convenient to make this n minus 1 as well. If I didn't have an n minus 1 there, I could do n minus 1 or n plus 1 on the negative 1. It would be equivalent. It wouldn't make any difference. So this is one way to see this written. Another way to see this written would be to combine the fact that these have the same exponent here. And you could actually write this then as the negative 2 to the n minus 1 because they're both having the same effect. A lot of times you'll see the 1/8 written in front instead of behind. There's no need to recreate the wheel on this every time. Every time you have a geometric sequence, you're going to have a term here, raised to the power, and the power is always going to be n minus 1. You may have a negative in there or not in there. That may or may not happen. And it may not always start that the first value is positive and the second value is negative, so you may have to work around with a little bit of that. But you're always going to have this thing, this term, raised to the value n minus 1. That term has a special name. We call it a common ratio. And I think we're going to get to this later. Your book actually uses just the term ratio for it instead of common ratio. But that is what it's called. You're also always going to have the first term, in this case it was 1/8, written as the coefficient in front of the power that you're raising and stuff, the ratio raised to the power. So that's always going to be there as well. Let me show you, I didn't have this written in here, although it would be a good idea for me to do an example real quick of one of these. Let me do an arithmetic sequence for you. Just write this to the side. Let me find a slide that's clean and blank. All right. So let's do one that's sort of like the one I mentioned before, but we'll start with 3 and go like this. Okay. So I'm not multiplying every time. I'm adding. I'm adding the value of 2, right? So to get from one term to the next, we add 2. But there's lots of ways, again, just like the multiplication, to add 2. It depends on where I start. Here I'm starting with the number 3. If I started with the number -7, it would be a different sequence, right? Because I started somewhere else. So what we're doing, though, is we are repeatedly adding. Now, repeated multiplication has this exponent feature to it, right? I'm multiplying by something lots and lots of times. But what happens when you add something multiple times? If I add 3 plus 3 plus 3 plus 3 plus 3 plus 3, how can I do that faster? I multiply, right? If I add the number 3 7 times, I don't really want to add the number 3 7 times. I would much prefer to multiply 3 times 7. It becomes multiplication. Same thing's true with an arithmetic sequence. This value is called the common difference. It's the same thing we're adding every time. And we could subtract just as well. There's nothing different about it. So this value right here ends up being multiplied by the number n. Okay, but if I leave it like it is, this isn't going to work, right? What happens when I put the number 1 in on here? I get 2. Is my first sequence value 2? It's not. So the easiest way to do this is to then look at your first sequence value and figure out what you need to add or subtract to get it. What do you need to add or subtract to get the end of this? You need +1. You need 1 more. So if I add the number 1 to this then, and I put in the value of 1, I will get 3. And if I put in the value of 2, I will get 5. And you can check multiple ones of them to make sure you haven't made a mistake, but this is the process. So whatever the common difference is right here, in this case it was 2, it becomes the coefficient of n. And then you figure out how you add, or what you add rather, or subtract on the end by simply looking at the first term. How far am I away? How far am I off? What do I need to add or subtract to make it the first term? Okay, does that make sense? Okay. I know you guys can handle that because I teach that to the elementary math students. And you guys are math majors and science majors and stuff, so you've had a lot more math than they have. All right, let's take a look back where we were then. All right, we're going to talk about some ideas of these sequences next. The first idea we're going to talk about is convergence. So the sequence, and this is a way of writing it, a sub n, where n starts at n sub 0, the first term, whatever it is, and it goes on infinitely. So that's the infinity you see on top. Converges to a number L, if and only if, for any epsilon greater than 0, there is a capital N, for which a sub n minus L is less than epsilon for every value of n greater than that capital N. If there's no such number L, we say that the sequence diverges. You've seen something similar to this before. What does this definition feel like? It feels like the definition of a limit, doesn't it? Yeah, it's because that's what it is. You're just saying that the sequence has a limiting behavior. It's doing something where it actually approaches a value. It's a limit. It's the limit of the sequence. And so we're doing the same sort of thing. So if you want to imagine having a sequence, one of the things to remember when you're dealing with sequences is that we don't have a smooth curve, right? It's just a sequence of numbers. So in theory, you've got something that looks like this. Right? They're not connected. We call this discrete, right? We have specific particular points, and that's it. And so this kind of a sequence looks like at least has the possibility where it's approaching, in this case, 0, right? So this is sort of what we're looking at. We can look at an equation in terms of its actual function values, and that will work, and we will do that in a moment and see sort of the relationship between them, but it isn't the same thing, all right? We really do have just a list of values, not an actual function that's continuous that we're working with. All right, so just like when we did, or when you did, limits back in the day, we would like to know if a sequence converges, just like we would like to know if a function had a limit. It's the same kind of a question. So we're going to see this particular function. So we've got 5n cubed minus 1 over 2n cubed plus 1. The process by which we're going to do this is going to look just like the limiting process you've done before. So what we're actually going to do is we're going to take the limit of this sequence. As n goes to infinity, and we're going to find out, does this sequence have a limit? That's what it means for it to converge. The sequence has a limit. So one of the ways you can do that, and we'll look at some other things later, is that you can actually multiply the top and the bottom value by something that makes the problem simpler. So what we're going to do is we're going to multiply by 1 over n cubed. And the reason we're going to multiply by 1 over n cubed is why? Do you remember? Do you remember? No, this was like second week of Calc 1, so a long time ago for some of you. Okay, take a look at the equation.
When you have 1 over and you put infinity in the limit, doesn't it go to 0?
Yeah, so like right now, the problem is that if we tried to sort of plug in something that gets infinitely large, the entire numerator gets infinitely large, right? The entire denominator gets infinitely large, and we can't do anything with it, right? You have sort of this idea of infinity over infinity. I mean, that's not a helpful sort of a situation. We'd like the infinities, if you will, to go away. Does that make sense? The nice thing about 1 over n cubed is, you see the n cubes in the problem? This is going to make the n cubed, the part that's making things go to infinity, go away, because when I actually distribute this to each of my terms, what does 5n cubed become?
5.
Right. Now remember, until we actually take the limit, we're going to write limit every time. So the first value simply becomes 5. Now, unfortunately, we still have n in the problem, because they're going to have to multiply that -1 by it, but we're going to just end up with 1 over n cubed. What's going to happen on the bottom?
2.
Right, 2 plus 1 over n cubed. All right, so far so good? Now, it doesn't probably look to you like it's really all changed that much, but that's actually changed quite a bit. The reason it's changed so much is because now, if I try to put infinity in, I'm not really plugging infinity in, but if I try to put things that are infinitely larger as we go in, the 5 stays 5. Agreed? The 2 stays 2. So those parts are okay. But what happens to this 1 over n cubed?
Zero.
It goes to 0. And that's helpful. So these pieces right here each go to 0, which means my limit becomes what? 5 over 2. So does it converge? Yes, it converges. And the reason we know it converges is because we actually found the value. Now, if at some point we had not been able to actually make the other pieces become 0, and the other parts actually turn into whole number values, like if we still had infinity on top and we had a whole number on bottom, then we would say it diverges because a part of the function was still going to infinity and the other part was going to 0, or staying at a constant value anyway. Okay? So this one is actually going to converge. All right, we have a few limit theorems, and you've seen these before in Calc 1, I believe, when you first talked about limits. The limit theorems start with sequences a sub n and b sub n that converge. Okay? So you have to first start with things that converge in order to make any of this work. So if you have two sequences that converge and you add them together, they still converge. If you have two sequences that converge and you subtract them, they still converge. Multiply, they still converge. And divide, they still converge. And there is one condition sort of happening down here on the fourth one. What do you think the condition is that has to happen to make this last one work? Yeah. This piece down here can't equal 0, because if that equals 0, then we're going to run into a problem, right? So we can't have this limit for b sub n of being 0. But other than that, which is, the one small sort of contingent case, everything else works sort of like we would want it to work. It has all the features that we would hope to have. All the features we don't necessarily have with derivatives, actually, that make things a little more complicated there. So we have all these same limit theorems that you actually had back in chapters 1 and 2 in your Calculus 1 textbook experience. But now we have them for sequences instead of for functions. Okay. I have one more theorem that we'll do today, and then we'll take a break and we'll pause till Monday. Did you guys get everything written down, or did I jump the gun? Are we all good? Okay. Theorem 1.2. Theorem 1.2 finally actually relates this idea of doing a sequence with doing a function. Notice, it talks about taking the limit of a function, f of x, and assuming that it exists. It has a function value that it exists, or limit value that exists, and then the value is L. If that happens, then we can actually talk about the function, and this is written in function notation because your book did it this way, but this is also the same as that sequence f sub n as a subscript. So if the function limit exists, then the sequence limit will exist as well. So that idea that I did just a minute ago where I drew these dots coming downhill and approaching, if I actually connected the dots, right, if the function itself, like if this is the image that I'm sort of picturing is that this is f of n is 1 over n. If I considered f of x is 1 over x, like this, and if the f of x function actually had a limit as x goes to infinity, which it does, right, it's limit 0, then automatically the corresponding sequence works. So if you have, what this is saying is that if you know that this works over here, if this one works, and you can put a little check mark here, then this automatically makes this work. You can't always go the other direction. And that's what the next example is going to show you, and we'll do that next time. Have a great weekend. I'll see you all on Monday.